Hi, this is a recorded lecture for the IB DP Design Technology, topic B2.2, Modeling and Prototyping. And we're going to be talking about CAD modeling today. This is part 2 in this series. From the IB, computer-aided design involves the creation, development, and analysis of a design outcome using computer software. Students must be able to construct and interpret surface, solid, and virtual models. So first of all, computer-aided design is defined as the use of computer software to aid the design process. CAD tools allow designers to visualize, modify, and evaluate their ideas in both 2D and 3D formats before any physical prototype is made. Students must be able to construct and interpret different types of CAD models. As with any models, we're trying to communicate and visualize our ideas, get feedback so that we can then iterate them further. This is basically the answer to all questions about modeling. So why would you use CAD modeling? Well, it's to visualize, get feedback, and modify. The first type of CAD model we're going to talk about is a surface model, a virtual model presenting the outer appearance and form, offering some machining data. Surface digital models contain no data of the interiors of the parts. So you can look at this model right here. There's no interior data. You can get some information, like for instance, what is this distance on this line or this line, but really that's about it. A CAD model used to represent the outer shape and contours of a design, often applied in styling and form development. One of the things that we would look for in a surface model is the aesthetic characteristics, and this refers to the visual and sensory qualities of an object or design that contributes to its overall appearance. Solid models are different. They are models that have clear representations of the final parts. They provide a complete set of data for the product to be realized. Complete 3D representations with mass and volume used for technical detailing, manufacturing, and simulations. And so you can see this, we can see the interior of this particular part, and the same with this. You've got all the data you would need in order to manufacture that particular part. Virtual models are digital simulations that may include motion, interaction, or functional testing of a design within a virtual environment. So for instance, this animation right here, it gives a good understanding of the workplace envelope of these robots so that the human technician is not getting into any sort of safety problems with the robots themselves. This is called augmented reality, and of course this is Pokemon Go, and what they would do is use your camera to show you the actual street, and then you have an augmented reality Pikachu who is floating in the street. CGI and also virtual reality are examples of virtual modeling. Finite element analysis, which is also abbreviated as FEA, is used to simulate how a part or assembly will perform under certain conditions. Students must be able to interpret the outputs from FEA. And you'll see this in a couple of different ways, which we'll talk about further. We'll see they're called heat maps, where the most problematic area is going to be in red and the least will be in blue. You also have the numeric scale, which will help you identify some of the displacements, in this case, in millimeters. Safety factors are another example of a condition that you can have in finite element analysis. And of course, you can see that in this case, we're above the target. So this is a safe beam. Finite element analysis is defined as digital model calculations and simulations of unknown factors in products using computer-aided design systems. So, for example, simulating the stresses within a welded car part. It's used as a method to analyze how a product or component reacts to the real-world conditions, such as stress, heat, vibration, and other physical forces. It helps designers and engineers predict performance, identify weaknesses, and refine designs before physical prototypes are created. So you can see again this heat map as this buckle is put together, and this would be displacement, I'm guessing. So why is finite element analysis important? It reduces physical prototyping, it saves time and cost by detecting design flaws early. It optimizes product performance and helps improve strength, durability, and efficiency. It enhances safety and reliability, ensures products meet required standards and regulations. It supports sustainable design by minimizing waste materials and identifying efficient design structures. And I'm guessing what we're looking at here is the reaction to heat on this part. So how does FEA work? First of all, you need to create a model. So the product is broken into small elements forming a mesh. You apply loads and constraints, so forces, pressures, and heat conditions are simulated. The computational analysis, the system calculates how elements deform or react, and results need to be interpreted. So designers evaluate stress distribution, deformation, potential failure points, and safety factors. Finite element analysis always has a visual representation. So the software typically provides color-coded visual representations of analysis results. Designers should be able to understand the color scales. Usually red indicates areas of high stress or temperature, while blue represents lower values. Deformation plots, these show how a part might bend or twist under a load, and contour lines, these indicate areas of equal stress or other measured quantities. There's also numerical data, so there's a maximum and minimum value, understanding the peak stresses or temperature in a design. There's safety factors, comparing calculated stresses to material yield strengths, and there's displacement values, assessing how much a part might deform under a load. So the IB wants you to know about rapid prototyping. So the increased effectiveness of rapid prototyping technologies enables designers to create complex physical prototypes for testing. Students must be able to construct and interpret CAD models suitable for rapid prototyping. So I'm showing you two types of rapid prototyping here. This is a subtractive method. These are actually tooth mills. So if you were to have a tooth replacement, you could have your dentist mill the tooth to the exact specifications of the tooth that you lost. And so this is subtractive because you're going to be taking away material. This is an additive manufacturing method, and it's 3D printing, of course. And you can see that you can 3D print quite complex shapes. So rapid prototyping is defined as a group of manufacturing techniques used to manufacture a physical object quickly for testing aspects of a product. It's typically 2D or 3D computer-aided design CAD models that are used. To produce functional and testable prototypes that support the iterative development process, designers must be able to construct and interpret CAD models that are suitable for rapid prototyping, ensuring the design is accurately represented and ready for physical production. This includes understanding the requirements of specific prototyping methods. Correct file formats are important. Tolerances and material constraints are also important. This is, of course, a laser cutter, and it's laser cutting acrylic. So, correct file formats. The common formats are STLs, OBJs, and STEP, and these are used to export CAD models for 3D printing and CNC machines, ensuring compatibility with the prototyping equipment. And so you can see STLs here, you can see G-code, I've got AI files, DXFs. These are all types of files, and you should know which one goes with which. So for instance, DXFs tend to go with CNC machines, and STLs are going to go with 3D printing. Tolerances are the acceptable variation in a part's dimension, important for ensuring that parts fit together properly during assembly or testing. And so you can see here some information about tolerances and clearance. And this is really important whenever you're 3D printing or laser cutting or CNC routing, if you want things to press fit or friction fit. Material constraints are the limits of what materials can be used with different prototyping methods. So plastics for 3D printing, metal for CNC, which affects strength, flexibility, and cost. You also need to pay attention to the different forces that the parts will be under. So compression, tension, torsion, deflection, and shearing are all important considerations. Now, the iterative design cycle, the act of repeating a process with the aim of approaching a desired goal, target, or result. Each repetition of the process is also called an iteration, and the result of one iteration are used as the starting point for the next iteration. And you should definitely watch this video. It's about Dyson and how he invented the vacuum cleaners that we have today. So it's a very important video. It's a very important idea. And just it really points out the number of iterative designs that Dyson went through in order to get from his first initial concepts into what we have today. Thank you for watching.